Now let us find the process on how we can find the inverse of a matrix by Gauss-Jordan elimination. That is, we are applying now the elementary row operations that you have learned last time. So let A be a square matrix of order n. Write the n by 2n matrix that consists of A on the left and the n by n identity matrix I on the right to obtain this matrix A that has been adjoined with I. No? We call the process as adjoining matrix I to matrix A. If possible, row reduce A to I using elementary row operations on the entire matrix AI, A adjoined with I. So the result would be that is as you go on with your elementary row operation and using your Gauss-Jordan elimination, the left side of the matrix, which used to be A, is now transformed into an identity matrix, whereas previously the right side of the matrix being I is now transformed into the inverse of A. If this is not possible, then A is non-invertible or singular. And then you simply check your work by multiplying to see that A times the inverse of A equals I is equal to the inverse of A times A. So for example, how do we find the inverse of the 3 by 3 matrix A? You have 1, 1, negative 6, negative 1, 0, 2, 0, negative 1, 3. So first of all, we adjoin A by the identity matrix. So we have here, we're able to adjoin I with A and then perform the elementary row operation. So we already have a leading one and we only need to transform this to 0 or eliminate it so that uh, we can have um, the number below 1 to be 0 and 0 and then make sure that um, this is converted to a leading one if we have an invertible matrix, and also this one to be 0 and this one to be 1. That is, if the matrix A is invertible, then applying the row operation will transform A into an identity matrix. And while we are doing it, the right side, um, the adjoint matrix here, which is identity matrix, is also transformed as we go along with the elementary row operation. So beginning with the first operation, which is adding the, let's say if I multiply row 1 by negative 1, say negative of row 1, add that one with your row 2 to be your new second row. Obviously, this one will be negative 1 plus 1. This will be 0. And negative times negative 1 will be positive 1. So this will be 1. And then still negative 1. This one will be negative 1. And then this is still 1. And then this is 0. Okay, so that the second row becomes 0, 1, negative 1, negative 1. So we can actually check it here. 0, 1, negative 1, negative 1, 1, 0. Now we have this 0. We need to change this now to 0. Say we multiply row 1 by 6. So that is 6 times of row 1. Add that one with row 3 to change your row 3. So that this becomes 0. And you have negative 6 plus 2. This one becomes a negative 4. And this one is still 3. You have 6 here, and then still 0 here, and then still 1 here. So we will come up with the resulting matrix to be 1, 0, 0, negative 1, 1, negative 4, right? So you have negative 4, and then 3, 6, 0, 1. So now we will have your 1, 0, 0, 1. We need to convert it to 0 now. So if we multiply row 2, okay, by 4, if we multiply row 2 by 4 and add it with row 3 to give us the new third row, then we will have, say, 4 plus negative 4 will be 0. 4 times negative 1 is negative 4 plus 3. You have negative 1. And you have 4 times negative 1 is negative 4 plus 6 is positive 2. 4 times 1 is 4 plus 0 is 4. 4 times 0 is 0 plus 1, you have 1. So you already have 1, 0, 0, 1, 0. So we need to convert this to positive 1 by simply multiplying negative 1 to your R3 so that this becomes 1, negative 2, negative 4, negative 1. Remember that this used to be our A, this used to be our I, and notice that the left side, okay, is already in, if this is, we remember that this is just adjoint matrices, so the left side is already in row echelon form. So proceeding with the backward phase, for the Gauss-Jordan elimination, we can convert this to 0 as well as this one. So say adding row 2 with row 3 to give the new row 2. This one is changed to 0 as well as the entries here are also changed. And then we need to change this to 0 now by adding row 2 and row 1 to be the new row 1. So this becomes 0 and then you have 0 and then simply adding up row 2 with row 1. So we will have negative 3 plus 1, that would be negative 2. Negative 3 plus 0 is still negative 3. Negative 1 plus 0 is still negative 1. And notice that the left side, this used to be our matrix A, is now our identity matrix. And notice that this used to be the identity matrix is now transformed into what we call the inverse of A. So the inverse of A is this one. We have negative 2, negative 3, negative 1, negative 3, negative 3, negative 1, negative 2, negative 4, and negative 1. You can be sure that this is the inverse of A if you check it using this equation. That is, the product of A and its inverse is I. The product of inverse of A and A is also I.